till now what we have done, we have seen some iterative methods and some elimination methods. What we have seen also some of the merits and demerits of these methods, and possibly what is interesting to see is that is it a viable option that we combine the elimination methods with the iteration methods, and that is indeed possible. Let us consider an example or a particular method which does it, that is called as line by line TDMA. So, we have earlier seen that the TDMA is a very efficient elimination method and it has the computational complexity of the order of n. At the same time, the problem or rather the limitation with TDMA is that you cannot use it directly for problems which have the corresponding coefficient matrices with more number of diagonals than 3. Like if you have a 2 dimensional discretization with 5 diagonals involved, in such cases, that is if you have a pentadiagonal matrix, then you cannot directly use the TDMA. So, why it is so? If you consider a domain usually in finite volume method, what we do, if we have the control volumes, then we consider grid lines like this which run midway between the control volumes, and these the points where these grid lines intersect, these are the grid points. Plus you also include grid points at the boundary to incorporate the boundary conditions. These points are also located on the grid lines. You have seen that very purposefully the grid layout is such that corner points are avoided, because corner points are points of singularity, so to say. If you for example take an instance where let us say that it is a heat transfer problem, this boundary is at a temperature of 100 degree centigrade, this boundary is at a temperature of 0 degree centigrade. The question comes that what is the temperature of this corner? Can it simultaneously be 0 degree and 100 degree centigrade? It can't be physically like that. So, these are certain interesting situations. I mean, these are the weak points in the analysis and we always try to avoid these weak points, and to avoid that ambiguity you see that you do not have any grid point really actually lying on this one. So, you will consider this grid point to be at 0 degree centigrade, this grid point to be at 100 degree centigrade, this point, this is not a grid point, this point what we do not know, God knows. Okay. So, I mean this can be a big dilemma, that if you see, this is where there is a weakness in the problem formulation. This is not a weak formulation, this is actually a weak formulation in literal English. So, if you see that when you have a particular temperature specified at this boundary and particular temperature specified at this boundary, What will be the temperature at this point? Think about it, it is not a straightforward answer. If you say that, well, it will be 0 plus 100 by 2 or something like that, that is just a heuristical statement. I mean, it has no basis, no scientific basis, but at least during the formulation we have no problem because this is not included as a part of the gridding system. Now let us see that how we intend to solve this problem as a solution of system of linear algebraic equation perspective. If you consider any grid point, it has 4 neighbors, interior grid point will have 4 neighbors, boundary will have less number of neighbors. So the grid point plus the 4 neighbors will form 5 elements of 5 diagonals. The grid point will contribute to the main diagonal and the other points to the immediate next diagonals adjacent to the main diagonal. So it is a pentadiagonal system. Still, let us say you want to use a TDMA. So you have to then convert the pentadiagonal system into a tridiagonal system. So tridiagonal system could be there if it was a one dimensional layout with grid points like this. That means in this example multidimensionality is bringing the deviation from the tridiagonal system. So what you can do, you can take it as a pseudo tridiagonal system. How? Let us consider this particular grid line. When we consider this particular grid line, we traverse along this grid line, and if we are interested to solve for, let us say, this grid point, then let us identify that what are its neighbors. It has these 4 neighbors. So the double ticks are representatives of the neighbors of this point P. Out of these, if you consider the horizontal line, the 3 are there in the same horizontal line, but 2 are there, this one and this one, these are there away from the horizontal line. So if somehow you would have known the values of the variable at these 2 points, then it would have been a pseudo tridiagonal system if you would have known these values. Now how do you know? You do not know because you do not have the solution. What best you can have? You can have a guess value or the most recent solution from an iterative scheme. So if you make an initial guess for the all the grid points and you start with the solution of this line, then you take the neighbor values, these double tick ones with the question mark, these are the neighbors away from the horizontal line, you take these values as the values from the recent iteration. So then your unknowns boil down to 3 for each grid point and it reduces to a pseudo tridiagonal system. So then you solve for the TDMA along this horizontal line. Once it is done, you go to the next horizontal line, this line. In the next horizontal line now, if you consider this grid point which we have already marked, it has its neighbors, 4 neighbors. I am just taking one example grid point for each horizontal line, but there could be several such grid points, just one example we are taking for each horizontal line. So when you take this horizontal line, you have again these 3 grid points located on the same horizontal line and these 2 located offset from that. Out of that, the upper one you can take from the previous iteration and the lower one you can also take from the previous iteration which has been solved immediately before this one. So, the most current one you can take, the upper one not the most current one because that line has not yet been solved. So, that you can take the previous iteration value, the lower one you can take the current iteration value. So, then you can solve for the TDMA along the next horizontal line. So, you have traversed, so what you are basically doing, you are having two mechanisms, one is a traversing mechanism, you are traversing along each horizontal line, and then another is a sweeping mechanism, that is you are sweeping one horizontal line after the other. So, you are sweeping the horizontal lines in a particular direction. So, in this way what you are basically doing, remember that what is the physical essence of solving a CFD problem? A physical essence is how quickly you can make your boundary conditions propagate in terms of their effect within the domain. So, you have a boundary condition here say 0 degree centigrade. So, in each step this effect is propagated by this distance into the domain. In this way once it is wholly swept, then this effect traverses to the other end. So, if you can make this effect traverse quickly, there are certain cases where the effect needs to be traversed quickly to achieve a fast convergence, and that can be done in several ways, we will come to that. But what we can recognize here is that the first thing, that we are applying the TDMA one line after the other. Then once we are considering TDMA along a line, then all the neighbors which fall for those corresponding lines, the corresponding values are taken as the most recent iterates. So, these are the essential features or essential points. So, apply TDMA along chosen lines. During this take values of the other neighbors as recent iterates. So, what you can see that in this way the boundary condition, effect of the boundary condition is propagating from one boundary to inside the domain, but the left boundary also has some boundary condition, and in this way the boundary condition is propagating from bottom to top, but what happens from left to right or left to other directions. So, what you can do is you can alternate these sweep and traverse directions. So, for example, for one set you have considered that you are taking horizontal lines for TDMA, then in the next set of iterations you consider the vertical lines as the lines on which you apply the TDMA and sweep along this direction. So, you alternate the directions of sweep and traverse, so that effects of all the boundaries may be propagated inside the domain in an effective way. So, alternate sweep and traverse directions so that effects of all boundaries may propagate inside the domain in an efficient way. So, we can see that this example is a combination of iteration and elimination. So, you have essentially an iterative environment where you consider initial guesses for each grid point, but then when you are solving along lines, then along each line you are applying TDMA, which is an elimination method. So, it is a combination of elimination and iteration method. Now, these types of switching directions is many times used in CFD in different methods. There is a method called as ADI method, alternating direction implicit. The idea of this is straightforward. The objective is again, like if you alternate the directions of your solution, your use of the TDMA or the elimination method, then you allow the conditions at all the boundaries to propagate in an equally effective manner to inside of the domain, rather than having a bias towards certain boundary which is not the case that you want. There are certain cases where a bias to one boundary is what is intended, like if you have a domain like this where these three boundaries are insulated and this boundary is subjected to a particular temperature, say T star at time equal to 0. So, it is the effect of the change of the temperature at this boundary that should propagate inside the domain. So, you can have this as the sweep direction, but this is a special case rather than a general case. In a general case you will have effect at all the boundaries equally important, if not unequal. So, then you expect it to be alternately directed in terms of the sweep and the traverse, or you design it to be like that, so that in the most general case also you have the effect of all the boundaries propagating efficiently inside the domain. In the alternating direction implicit method, the same principle is used. So, what is done is you have the total in a, so this is used for an unsteady problem. In an unsteady problem you have the total time interval as delta t, each time interval total delta t. So, here what is done is this delta t is divided into two parts, delta t by 2 and delta t by 2. So, the elimination method is applied over delta t by 2, first delta t by 2 in one direction and in the next delta t by 2 over another direction. So, the basic principle, so the direction of implementation of the elimination method is alternated in every half time interval. Because it is alternated, that is why it is called as alternating direction implicit. So, you can use a fully time implicit scheme, but in that you have a delta t by 2 and delta t by 2 as half of the time interval. So, in this you have a particular direction of implementation of elimination method, and here the direction is reversed. Yes, that means if this was along x direction, this would be along y direction. So, if you implement it along x, so if you have horizontal lines along which you solve for the elimination method, then in the next case you reverse it. So, you make it reverse means like the other direction. So, if this is x direction, this will be y direction, like that. So, we have seen some examples of elimination method, some examples of iteration method, and some examples where we have combinations of elimination and iteration methods. Now there are certain methods which are neither elimination methods nor iteration methods, but some methods which are fundamentally based on optimization techniques, and those methods are known as gradient search based methods. So we will now get into the gradient search based methods. So this method what it tries to do is, if you have a function f, you know that the gradient of the function represents the maximum rate of change of the function. So it tries to search a solution of a system of equation by moving into the gradient of a function, and how it does, to understand that, let us consider an example. Let us say that we have a function f. Our objective is to solve the equation system of equations Ax equal to b. So f is equal to half x transpose x minus b transpose x plus c, where c is an arbitrary constant. There are two very important restrictions that are imposed. One is A is symmetric and the other is A is positive definite. So you can use this method only with these restrictions. The next objective is to find out the condition for minimum of f. So minimum of f implies that the gradient of f must be 0. Let us write in a expanded way what is f. So half x transpose will have x1 x2 in this way up to xn, a11 a12 in this way a1n, a21 a22 in this way a2n, an1 an2 in this way ann. This is half x transpose Ax minus b transpose b1 b2 in this way bn into x plus c. What is the gradient of f? Del f del x1 del f del x2 in this way del f del xn. So let us find out first what is del f del x1. To do that, maybe let us do one more step to simplify f. So let us check the dimensionalities of the system for matrix multiplication compatibility. This is n by n, this is n by 1, and this is 1 by n. So, the final result is just a scalar 1 by 1. So, let us write this x1 x2 up to xn, then multiplication of these two. So, first row with first column a11 x1 plus a12 x2 in this way a1n xn, then second row with first column a21 x1 plus a22 x2 in this way plus a2n xn, in this way. The last one is an1 x1 plus an2 x2 plus ann xn. You can expand one more step if you want. So, f is equal to half x1 into a11 x1 plus a12 x2 in this way plus a1n xn plus half x2 a21 x1 plus a22 x2 this way plus a2n xn in this way plus half xn an1 x1 plus an2 x2 plus ann xn minus b1 x1 plus b2 x2 in this way bn xn plus c. So, what is del f del x1? So, for the first term you use the product rule. So, it is half into a11 x1 plus a12 x2 plus in this way a1n xn, then plus half x1 into the derivative of this term a11. So, half a11 x1 from the next term what will come out? You have x1 has the, this is the term only which has x1. So, the corresponding derivative is half a21 x2. So, a11 x1 plus a21 x2 in this way plus an1 xn, that is this term minus b1, c is the constant. Now, because A is symmetric, A equal to A transpose, that means A12 is equal to A21, AN1 is equal to A1n. So, in place of A21 it is A12, in place of AN1 it is A1n, like that. So, then the term in this bracket and the term in this bracket they become the same. So, it becomes A11 x1 plus A12 x2 plus in this way A1n xn minus B1. So, you can write this as A11 A12 in this way A1n into x1 x2 xn minus B1. Similarly, what will be del f del x2? Here in place of A11 it is A21 A22 in this way A2n into x1 x2 up to xn minus B2. So, if you write what is gradient of f, that is del f del x1 del f del x2 in this way del f del xn. So, that you can assemble all these rows, so that finally you will get A11 A12 in this way A1n for the first row, A21 A22 in this way A2n for the second row, finally AN1 AN2 in this way ANn for the nth row. So, the first row is for del f del x1, second row is for del f del x2, in this way nth row is for del f del xn. You can see that in symbolic form this is nothing but equal to Ax minus b. So, setting grad f equal to 0 is as good as setting Ax minus b equal to 0 or getting the corresponding solution as the solution of the system Ax equal to b. So, in other words we can say that getting a solution of Ax equal to b is as good as extremizing the function f. When we say extremizing the function f, we have set the condition grad f equal to 0, it could either be a maxima or could be a minima. The next stage, in the next step what we say that what we do here is indeed a minimization of f but not a maximization. How do we show that what we are doing indeed corresponds to a minimum of f but not a maximum of f? That is the next thing that we would see. So, the next question that we would like to answer is why minimization and not maximization. So, for that let us again write what is f, half of x transpose Ax minus B transpose x plus C. Let us consider a vector E and find out what is f x plus E. If we can show that this is f of x, if we can show that f of x is the minimum of all possible arguments corresponding to this one, that is f of x is less than f of x plus E for all E, that means that f of x is a minimum. Okay. So let us write what is f of x plus E. This is half of x plus E transpose A x plus E. Remember, E is any arbitrary vector, minus B transpose x plus E plus C. So let us expand this. This is half x transpose A x plus half E transpose A x plus half x transpose A E plus half E transpose A E minus B transpose x minus B transpose E plus C. From this we can isolate certain terms. We can isolate half x transpose A x minus B transpose x plus C, because this is f x. Next we can make certain simplifications. Remember, E transpose A x is a scalar. So it is just like x transpose A x, in place of x it is E. Similarly, x transpose A E. So you can write x transpose A E as follows. So this is same as x transpose A E transpose. Transpose of a scalar is the scalar itself. Then you can use A into B transpose equal to B transpose into A transpose. So this will be A E transpose into x transpose transpose. So this is equal to E transpose A transpose x. Because A is symmetric, A transpose is equal to A. So this is E transpose A x. Because you have symmetric A, this implies A transpose equal to A. So this term becomes E transpose A x. This term has, so this is half E transpose A x, this term another half E transpose A x. So total together it becomes E transpose A x. Then let us consider this B transpose E. B transpose E is B transpose E transpose, because this is also a scalar. So this is equal to E transpose B transpose transpose. So E transpose B. Now if you combine all these terms, we can write f x plus E equal to f x plus E transpose A x minus E transpose B plus half E transpose A E. because Ax equal to b, so you have this equal to 0. So it becomes Fx plus half E transpose Ae, because A is positive definite, E transpose Ae is greater than equal to 0 for any arbitrary E. So this is greater than equal to, sorry, this is greater than equal to 0 for arbitrary E, since A is positive definite. So from here what follows is that Fx plus E is greater than equal to Fx. That means any other functional argument with which is different from x is greater than or makes the function f greater than the function with argument of x. So Fx is a minimum and not a maximum. Okay. So what we can summarize from this discussion? We can summarize that if we construct a function f as half x transpose Ax minus b transpose x plus c, where A is a symmetric and positive definite coefficient matrix, then minimization of f corresponds to the solution of the system Ax equal to b. That is what we can summarize from this. So based on this technique, therefore one may go for a solution of the system Ax equal to b not in a direct way, but in an indirect way with an approach so as to minimize the function f by constructing the function f and then minimizing that. And because it tries to traverse in a direction of the gradient of f and set that to 0, it is called as a gradient search method, because it is searching the direction of the gradient and setting it to 0 so as to get the solution of the system of algebraic equations. Now this gradient search method has different varieties. We will not go into the details of the gradient search methods in this particular course, but what we will try to do is we will try to consider one or two very basic types of gradient search methods, and with very simple illustrative examples try to understand the concept that is there behind implementation of this method. And the first of that kind is known as the steepest descent method. We will try to learn this method through a very simple example. Let us say that we are interested to solve example, solve Ax equal to b where A is equal to this one and b is equal to 1 1. So what we will do is we will first follow the steps that we have identified through the initial prescription of the minimization problem. We have to first specify a minimization problem of a function. So let us construct the function f. What is this? Half x transpose x minus b transpose x plus c. So, half x1 x2 minus 1 1 x1 x2 plus c. So, this becomes half of x1 square plus x2 square minus x1 minus x2 plus c. So, f represents a family of functions depending on the choice of c. So, what does this family represent corresponding to f equal to 0? What does f equal to 0 represent? So, let us do a bit of coordinate geometry for that. It is a 2-dimensional situation, so we can interpret it geometrically in a very simple way. So, we have half of x1 square minus 2 into x1 plus 2 square sorry 1 square plus x2 square minus 2 into x2 into half plus half square plus c. Then what we have added extra, half plus 1/4, that is 3/4. So, we subtract 3/4, that is equal to 0. So, x1 minus 1 whole square by 2 plus x2 minus half whole square is equal to 3 by 4 minus c. You can specify the choice of c by forcing this function to pass through a particular point. For example, if you allow it to pass through 0 comma 0. So, if f passes through or satisfies 0 comma 0, then half plus 1/4 is equal to 3/4 minus C. So, what is C? C is 0. Remember, choice of C is arbitrary. So, you can allow your function to satisfy a particular set of points and then find out the value of C accordingly. Next, what we will do is we will try to make a sketch of this function. So, the function is like x1 minus 1 whole square by 2 plus x2 minus half whole square by 1 is equal to 3/4. So, x1 minus 1 whole square, if you can multiply both the sides by 4 by 3. So, here it becomes 2 into 3 by 4. So, 3 by 2 plus x2 minus half whole square by 3 by 4 is equal to 1. So, what does it represent? It represents an ellipse in the x1 x2 plane. So, root over 3 by 2 whole square, then root over 3 by 4 whole square. So, x1 minus x1 minus alpha whole square by a square plus x2 minus beta whole square by b square equal to 1, where alpha is 1, beta is half, a is root 3 by 2 and b is root 3 by 4. So, what is the center of the ellipse? 1 comma half. So, let us try to make the sketch as accurately as possible, of course, a rough sketch. So, x1 equal to 1 and x2 equal to half. So, 1 comma half. So, the major axis will be laid out along this direction, minor axis will be laid out along this particular direction. Okay. So, x1 minus 1 by root 3 by 2. So, a is root 3 by 2. So, maybe some distance like this. So, if we make a sketch of the function, I am just making the sketch arbitrarily, but it should be consistent. It passes through 0 0. That is how we have constructed the function f. Okay. So, let us make a plan by looking into the geometrical form of this function. See, this is a very simple system. By looking into the solution, looking into the equation, you can see that it is x1 equal to 1 and x2 equal to half, that is the solution. I have purposefully chosen this very simple system because it will illustrate us something important. What it will illustrate? 1 comma half is the solution that we have seen from the system. Let us say that we start with the initial guess point as 0 comma 0. So, we start with this point and we intend to hit this bull's eye. when we start with this point and we intend to hit this bullseye, we will not be able to do it in one shot, because starting from this point what is the direction in which we will be moving? We will be moving in the direction of gradient of f, that is the maximum rate of change of f till it comes to a minimum. So the gradient of f, when we consider at this point, what it will represent? It will represent the normal direction to the curve, but normal direction to the curve is not going to directly point to the center, because this is not a circle. If it was a circle, it would have directly pointed towards the center. Because it is not a circle, it will not directly point towards the center. So what it will do? It will point towards some direction which is not exactly this one. So we will move in certain direction, and the direction is what? The direction is something very special. Why it is special? Gradient of f is what? It is ax minus b, that is what we have already found out. So that is nothing but equal to minus r, where r is the residual. So it has also something to do with the residual. We have defined the residual as b minus ax. So we are moving along the direction of the residual at a particular point, we move by certain distance and then we will stop and change the direction, because eventually we have to reach here. So where to stop and change the direction and take a new direction in a way with an effort to reach here is the next objective for us to learn, and that we will take up in the next class. Thank you.